All right, let's talk about something in AI that sounds like a simple bug, but it's really one of the deepest, most fascinating paradoxes out there. It's called overfitting. And what's so weird about it is how the very thing that makes an AI seem so smart, its ability to learn, can also be its biggest flaw. So, yeah, let's get right into it. But before we get all technical, I want to start with a question for you. Just think about this for a second. What's the real difference between just recognizing a pattern and actually understanding the reason behind it? I mean, when an AI predicts the next word perfectly, is that real intelligence? Or is it just the world's most advanced parrot? This, right here, is the core of the whole overfitting puzzle. Okay, so what is overfitting officially? Well, the textbook definition is pretty straightforward. It's when a model learns its training data a little too well, like it gets completely obsessed. It doesn't just learn the important stuff. It memorizes all the noise, the random flukes, the irrelevant details. It basically becomes a world-class expert on its homework, but then completely bombs the final exam. You know, the best way to think about this is with a classic analogy. The student who just memorizes everything for a test. Imagine they've crammed the study guide, memorizing the exact wording of every single answer. If the test asks those exact questions, they'll get a perfect score. But what happens if the teacher throws in a new question, one that requires them to, actually apply the knowledge? Yeah, they're toast. They have no idea what to do. That's overfitting in a nutshell. So for a really long time, people in machine learning had a pretty clear way of thinking about this. It was seen as this classic balancing act. It was all about finding that perfect middle ground. And this whole framework is called the bias-variance tradeoff. Think of it like a spectrum. On one end, you've got high bias, or underfitting. The model is just too simple. This is our student who didn't study enough, maybe just skim the chapter titles. Then, on the complete other end, you have high variance. That's our overfitting. This is the student who memorized everything, right down to the typos and the coffee stains in the textbook. So for decades, the name of the game for engineers was to find that perfect sweet spot right in the middle. You wanted a model that was complex enough to get the job done, but not so complex that it started memorizing noise. That was just how it was done, the gospel, really. But then, things started to get weird. Around a decade ago, the old rules just stopped working. This is where our whole story takes a sharp turn, because with the rise of deep learning, that neat and tidy balancing act we just talked about, it got completely thrown out the window. And this leads us to a much deeper and honestly, a way more interesting question for today's AI. Is the real problem that these models are learning too much, or is it that they're understanding too little? Okay, so here's the central mystery. Modern AI models are just huge. They're massively over-parameterized. That's a fancy way of saying they have way more knobs to turn, parameters, than they have examples to learn from. I'm talking billions of parameters. Now, according to all the old rules, these things should be the absolute worst overfitters imaginable. They should be completely useless on anything new. But they're not. They're actually amazing at it. So what is going on? Well, this huge contradiction forced researchers to dig deeper, and what they found was bizarre. It's a totally counterintuitive phenomenon that just flipped our whole understanding of learning on its head. This is where we get to the double descent twist. So let me just throw a crazy idea out there. What if the whole sweet spot thing was wrong? What if the way to get a better model wasn't to avoid overfitting, but to lean into it, to blow right past that overfitting peak and just keep making the model even more complex? Okay, check this out. This graph shows something that just shouldn't happen according to the old rules. This is the double descent curve. Just follow the line for test error. As you make the model more complex, moving from left to right, the error goes down. Great. Then it hits that point where it shoots back up. That's that classic overfitting peak we talked about, right where performance gets terrible. But, and here's the wild part, if you keep going, if you make the model even more complex, the error starts to go down again, a second descent. It's incredible. So how on earth is that possible? Well, the leading theory is that when a model gets this big, this over-parameterized, it actually gets a new superpower. It has so much capacity that it can basically do two things at once. Part of the model is dedicated to just brute force memorizing every single detail of the training data, noise and all. But then it uses the rest of its enormous brain power to build a much smoother, more general version of the world that can actually tell the difference between the real information and all that noise it memorized. This whole double descent discovery just blew the doors open on a new way of thinking. It turns out, learning doesn't just stop when the model starts overfitting. In fact, for these huge models, that's when some of the real magic starts to happen. This is what we're calling learning after overfitting. And researchers found an amazing word for this. They call it grokking. It's straight out of science fiction. Grokking is this bizarre moment where a model has already achieved 100% on its training data, it's totally overfit, but you keep training it anyway. And then suddenly, out of nowhere, it's like a light bulb goes off. Its ability to handle new data just skyrockets from basically 0 to nearly perfect. It's like a sudden moment of true understanding. So here's how they first saw this happen. Researchers at OpenAI were training these small models on simple math problems, like addition. And at first, the model did exactly what you'd expect. It just memorized the answers. 2 plus 2 is 4, 3 plus 5 is 8. Perfect memorization. But they didn't stop the training. They just let it keep running and running. And then bam, all of a sudden, its accuracy on new math problems it had never seen before shot through the roof. It wasn't just memorizing answers anymore. It had somehow figured out the rule of addition. But why does this grokking happen? Well, one idea is that making the model super complex actually forces it to simplify its strategy. Think of it like this. If you have 1,000 different advisors or parameters, all shouting different things, you can't listen to all of them. You're forced to only pay attention to the few who are making the most sense. This chart kind of shows that. As you add more and more of these noise predictors, the model starts to ignore them. It's a weird form of self-regulation. And the paradox is, you get this beautiful simplicity by adding more and more complexity. Here's another really cool way to think about it. Maybe the model isn't choosing between memorizing and generalizing at all. Maybe it's doing both. So, step 1, the AI doesn't look at the data as is. It creates its own custom map, or feature space, for the data. Step 2, on that map, it just memorizes where everything is. Pure memorization. But here's the magic. Step 3, to figure out something new, it just finds the closest thing it already memorized on its custom map. And because the map itself was built for generalizing, this simple nearest neighbor trick works incredibly well. Okay, so we've gone on quite a journey here. We started with what looked like a simple bug, then we saw this bizarre double descent curve, and now we're talking about whole new theories of learning. So, what does this all actually mean? How should we think about AI now? That brings us to our final section, which I'm calling the statistical mirror. So let's go back to our student who just memorizes everything. The old school thinking was, nope, they'll never truly understand. It's just empty memorization. But double descent and grokking, they suggest something else entirely. They suggest that if our student didn't just memorize one textbook, but 1,000 or 1,000,000 and just kept at it, maybe, just maybe, through that sheer overwhelming amount of memorization, they would start to see the deeper patterns. Maybe they could actually stumble their way into genuine understanding. And that forces us to ask a really tough question about what we're even building here. Are we creating things that can actually think? Or are we just building the most sophisticated compression algorithms in history? Is the AI learning the fundamental structure of reality? Or is it just getting ridiculously good at finding the most efficient way to pack up and spit back out all the statistical patterns we fed it? You see, if this new way of thinking is right, if the only path to real generalization goes through a period of complete overfitting, then that changes everything about how we should be using AI. It means our goal isn't to avoid overfitting anymore. It might be to embrace it, to push right through it, and to realize that what looks like a bug might actually be a feature, a necessary step towards a deeper kind of learning. So, we're left with this huge question at the end of it all. What is AI, really? Is it just a tool like a super smart hammer that does what we command? Is it a creative collaborator? Or is it just a statistical mirror? Is it just reflecting back at us an image of our own world, complete with all our knowledge, but also all our biases and all our noise? The overfitting paradox doesn't give us any easy answers. But what it does show us is that the line between learning too much and understanding too little, well, it's a lot blurrier and a whole lot more interesting than we ever thought.